Okay, good morning, everyone. Welcome to CS 206, Evolutionary Robotics. I think we have almost everybody here this morning. I'm Josh Bongard, the instructor. Josh is fine. And I can see on the call we also have Amanda Birchinger. Amanda is going to serve as the teaching assistant for the course. So what we're going to do today is talk a little bit about the logistics, about how this course is run. Some of you may have taken my human-computer interaction course before. This course runs very much like HCI. If you haven't taken my HCI class before, the way I run this class may be a little bit different from some of the others you've taken before. So we're setting aside today to make sure we're all on the same page about how this course runs, what me and Amanda will expect from you, and what you can expect from Amanda and I. So before we get to the logistics, though, I wanted to welcome you all back. I don't know about you, but this is my first class back, so it might take a little while to shake the rust off the gears and get back into class mode. I imagine that may be true for some of you as well. Obviously, we had a longer winter break than usual because of the current circumstances we are all under. I know you are all in different places, figuratively and metaphorically. I hope you're all well and rested and are able to dedicate some effort to CS 206. So just to talk a little bit about remote instruction, for better or for worse, we're all kind of used to this now, if not comfortable with it, at least used to it. One of the big challenges that you have all probably figured out is sort of it's hard to create a sense of community when we're not all in the classroom working and thinking about evolutionary robotics together. You don't have to turn your camera on if you don't. I know there's a social norm now about leaving the camera off, so be it. But I would invite you to participate in class as best you can. Please do type into chat at any time. If you have questions, I think on Teams can raise your hand if you have a question. I will keep an eye out for raised hands and pause and field any questions. So hopefully we can turn this more into a conversation than a lecture. So in that spirit, before we get started, if you wouldn't mind typing into chat whether you are a sophomore, junior, senior, or grad student. I think we have a pretty good, you can go ahead and type that into chat now. I think we have a pretty good mixture of all of the above. Okay, so we have a fair number of seniors and juniors. I know there are some grad students in this class. Great. Okay, wonderful. Well, nice to see you all here. Again, I wish we could be in the classroom together and I could get to know you in person. So be it. We will do the best we can. So again, we have a mixture of students in the class, and some of you have a little bit more programming experience than others, and so some of you may be wondering whether this is the right course for you. We're going to spend a fair bit of time on logistics and expectations today to help you be able to figure out, again, whether this class is right for you. Okay. Let's see. I guess we'll start at the top. I just want to go through the syllabus so we've all seen this. Obviously, we're meeting here on Teams Tuesday and Thursday morning. You'll notice in the syllabus here there's a link to the schedule, which I will put up at the beginning of class. Every morning, but these two documents you definitely want to bookmark and keep an eye on throughout the semester. They will keep you oriented about sort of all the logistics of the class, and the schedule will let you know where we've been, where we are, and where we're going. Okay. So I hold office hours Mondays and Thursdays. Office hours are organized in the following way. If you click on the link here, this will take you to a spreadsheet. You can see all of my office hours. So here's my upcoming office hour on Thursday at 11 a.m. There's instructions here about how to sign up for office hours. All you need to do is type your name in here, and that should not be struck out like that. You type your name in there, and then at 11 o'clock, I will DM you on Teams and invite you to a meeting just between you and we can chat on Teams. And then if, for example, Amanda wants to meet with me, she would put her name in there, which also should not be struck through. And so Amanda's waiting, and when I finish up with Josh here, I will strike through, and then Amanda knows she's next in line. I will DM Amanda on Teams and invite her into the meeting, and on we go. So you can sign up for this Thursday. Maybe you want to meet with me next Monday, and so on. If you arrive at the spreadsheet and you see there's a couple other students in line, just put your name at the end of the line, and if and when I get to you, I'll invite you into a one-on-one meeting on Teams. All good? Okay, that's office hours. Amanda has the same thing. You can sign up for Amanda's office hours through her spreadsheet, and she's holding office hours Monday afternoon and Wednesday early afternoon. Okay, so this is the blurb, hopefully, that you saw associated with the course. So what is this course all about? In this course, we're going to explore the automated design of autonomous machines using evolutionary algorithms. So there is a sister course to this course called Evolutionary Robotics, being taught by Professor Cheney. We're going to use evolutionary algorithms in this course, but it is not the prime focus of this course. So you're going to be implementing a relatively simple evolutionary algorithm and then using it to evolve robots to do various things. You'll notice right here at the beginning, there are two levels of automation that we're going to explore in this course. And this is sort of the signature of evolutionary robotics. The object, the thing that we are creating, is an autonomous machine. This is not going to be a remote controlled robot. It is also not going to be a hardware robot. There's no hardware in this class. We're going to be creating simulated robots in physics engines. But the robot itself is autonomous. The robot is going to be equipped with a number of sensors in which it draws information out of the world, transforms those sensor values through its internal brain into commands that it sends to its motors. The motors cause the robot to move. The moment that the robot moves, its relationship with its simulated world changes, and the values of its sensors change, which means the way it processes that information changes, which means the values that it sends to the motors change, the robot moves. This is known in robotics as sense, think, act. So it is closed loop. It is a closed loop system. The robot is a closed loop system in the sense that there is information flowing from the sensors to the brain to the motors. The motors impact the robot's body, which impacts its relationship to the environment, which again closes the loop by affecting the sensors, and around we go. Okay, so that's why it's autonomous. It's not being directed by someone or something else externally. These autonomous machines are going to be automatically designed by an evolutionary algorithm. We are going to see throughout this course how we can make as few assumptions about what the robot should look like and how it should behave. We're going to let the evolutionary algorithm figure that out for us. Okay, we'll come back to this idea many times throughout this course. Okay, this is a relatively broad course rather than a deep course. We're going to touch on a lot of different elements of computer science and engineering and biology, and we're going to cobble together all of those pieces to automatically design autonomous machines. I already mentioned we're going to talk about evolutionary algorithms or evolutionary computation. These are two phrases for the same thing. The robots are going to be controlled by neural networks. Again, there are a lot of neural networks classes here at UVM, so there is a machine learning component in this class for those that are interested in that. Obviously, we're going to have to learn a little bit about what robots are. We're going to look to nature for inspiration. How do animals move and survive in their environments, and can we learn anything from that for evolving robots? And finally, we're going to do a little bit of physics when we get into the nuts and bolts of physical simulation. Okay. The bulk of this course is Python programming. So regardless of your academic level at the moment, I'm assuming that everyone in this class has a fair bit of Python programming experience. If you don't, this may not be the right course for you. This morning, I'm going to assign the first programming project, which is going to be due a week from now. I would suggest, especially if you're not confident in your Python skills, get started on that programming project immediately. If you find yourself struggling with this first assignment during this first week, this is the reason why I assign it today. It gives you plenty of time to disenroll from the class and find another class that's better suited to you. If you're a junior, by all means, come back and see us when you're a senior and have some more programming experience. Okay. We'll talk more about that in a moment. Let's see. So there are undergraduates and graduates taking this class. The undergraduates are going to spend the first 10 weeks doing a series of 10 programming projects, and then carry out a pre-specified, in the last 4 weeks of the class, you're then going to take this code you've developed over the first 10 weeks, use it as a base to then carry out a pre-specified evolutionary robotics experiment. I have a whole menu of things you can attempt. You can also propose something of your own that's doable within about 4 weeks. The graduate students are going to also do the exact same set of 10 programming projects over the first 10 weeks, but in the remaining 4 weeks, the graduate students are going to formulate a research hypothesis, a question, and then they're going to develop additional code that sits on top of this 10-week code base to test their hypothesis. And I'll talk with the grad students about that later on. I left this note in here, sort of makes me nostalgic for the before times when we all met in person. We tried to make it a non-electronic class. Obviously, that's not possible in remote instruction. Okay. Lectures. I am currently recording the lecture. When we finish up this morning, I will upload the recorded video to YouTube, so you can go back and watch various parts of this lecture as many times as you like. This means, of course, that if you volunteer a question or you answer a question verbally during the lecture, it's being picked up by the recording, and so you are, by asking a question or speaking verbally, you are tacitly agreeing to being recorded, just so you know. Okay, Teams etiquette. I think we've all figured this out at this point. You're all muted. Thank you for that, just in case there's background sound. I would love it if you left your video on, but if not, that's fine. Okay, I think I already mentioned this already. Feel free to type questions into chat or raise your hand at any time. No problem. Okay. Let's see. Versions of the lecture slides are posted online before class on, I should say, this should not be Blackboard. This is on the schedule. So you'll see in the schedule there's a link now to today's set of lecture slides, which we'll get to in a few minutes. And there's some reading associated with today's lecture. We'll talk about that in a little bit. Okay. So what I suggest is to open and make a copy of that slide deck and then annotate it electronically as we go. If it's too much to annotate and listen to me at the same time, after the fact, make a copy of the slides, watch the lecture on YouTube, and annotate the slides as much or as little as you like. It definitely helps to absorb and digest the material if you are actively engaged in the material. Obviously, feel free to sit back and listen to these lectures Tuesday and Thursday morning, but you will probably only absorb so much. You figure out how to actively engage with the course material as we go. Okay. For most accommodation students, the fact that the lecture is available on YouTube later this morning should mean that you don't need a note taker, but if you do need some accommodations and you find the way I teach this class requires some accommodation, no problem, just let me know and I'm sure we can figure something out. Okay, I'm just going to pause for a minute. Any questions so far? Nope. Okay. So there is a textbook for this class. It's optional. I will be posting PDF excerpts from the textbook, and I will be embedding them in the schedule as we go. Here's one. So biologically inspired AI. Here's another PDF excerpt. Here's another PDF excerpt, and so on. So you do not need to buy the textbook. There is another optional textbook. This is a book that I wrote together with one of my colleagues, several years ago now, How the Body Shapes the Way We Think. It is optional. You do not need to buy this textbook. Thanks to the wonders of academic publishing, if you do buy this textbook, I make a grand total of $1. There are 60 people signed up for this class, so if I force everyone to buy a copy of my book, I will be $60 richer. So not much of a financial incentive for me to force you to buy the book. I would, of course, be honored if you did, but it's completely optional. Okay. Along the way, there will also be readings from the current literature, and again, they'll all be links to PDFs or web pages sprinkled throughout. So, a typical day like today, obviously we're all here together. We're talking about CS 206. When we finish up, I would set aside some time today to do the reading and possibly watch parts of the video lecture. Okay, let's see. So prerequisites, again, I expect junior standing or above. I think everyone is junior or above, so that's good. Programming experience, again, how much programming experience? That's up for you to answer for yourself. Okay. Grading scheme, you're going to be handing in various stuff along the way. If it's 1 day late, 25% deduction. 2 days late, 50% deduction. If you're handing something in 3 or more days late, you can hand it in, but you won't obtain any grade for it. Okay. The spine of this course are 10 weekly programming assignments. And you'll see, obviously, this is worth a big part of your grade. We're assigning the first of those 10 programming projects today. And if I go back to the schedule for a moment, there's the assignment. There's a link to that assignment, which we'll talk about in a moment. And you'll see that that assignment is due next Monday at 11:59 p.m. So it's due the night before the next class, which is Tuesday, Jan 21. And on Tuesday, I will assign assignment 2. Yeah. So each assignment takes 1 week. Pretty straightforward, right? Okay. Each of these programming projects is cumulative. It builds on the code that you wrote the week before. So like a math class, be very, very careful not to fall behind. If you do, then you have to implement the code for assignment I, but before you do that, you have to finish up whatever code you didn't finish for assignment I-1 the week before. It gets very difficult, especially as the semester wears on and you have more midterms and more projects and other classes. Be sure on Tuesday morning when the assignment is assigned to get started as soon as possible. Do not leave it to Monday night. Okay. Quizzes. So there are quizzes sprinkled throughout this course. This is just a gentle prod meant to make sure that you stay on top of both the lecture material and the reading material. So after each class on Tuesday and Thursday, I will post a multiple choice quiz on Blackboard. If you came to lecture and you do most of the reading, you should be able to take the quiz in 10 minutes or 5 minutes or less. It's obviously open book. You can take the multiple choice quiz with the YouTube video lecture open and the reading open. That's fine as well, whatever works best for you. The quiz is due by 11:59 on the day of lecture. So again, today, I will, when we finish up here, it's usually about noon, I will post the quiz on Blackboard, and it's due for you by 11:59 p.m. tonight. Thursday we'll have another lecture. There'll be more lecture material and reading. Quiz due Thursday night at 11:59 p.m. The material on that quiz will be drawn directly from the lecture slides and or the reading. If there's questions in chat and we have a discussion that goes off in a different direction, that will not be on the quiz. Okay. Again, just a gentle reminder, these quizzes are meant to be a gentle reminder to stay on top of the material as we go. Okay. The remaining part of your grade is a final project. So at the end of the 10th week, you will have a code base that allows you a code base in which an evolutionary algorithm is evolving simulated robots to do a relatively simple task. You then have the remaining 4 weeks to perform some kind of evolutionary robotics experiment, and I'll show you a few examples from past years in a few minutes. During those 4 weeks, you will be submitting weekly deliverables, which are demonstrating to me and the TA and I that you're making progress towards your final project. There will be a written report describing the experiment or your final project. And finally, there will be an oral presentation. So there is no final exam in this class. Instead, we use our 3-hour exam time for each of the 60 of you to give an oral presentation. 60 divided into 3 hours means you're going to have an entire 2 minutes or maybe 2 minutes and 30 seconds to present your work. It's not a lot of time. We'll talk about how that works towards the end of the semester. Okay. I already mentioned graduate students, you'll be doing something much more involved during those last 4 weeks. Okay. Last small part of your grade is participation. I will show you some data in a moment that shows that students that come to my classes tend to do better in my class. So you will notice finally on the schedule, in the very right-hand column here, there is a link to an attendance sheet. So when you arrive for lecture here on Teams each Tuesday and Thursday morning before lecture starts, or while lecture is starting, be sure to click on this link and find your name and type in that you are present. Okay. This spreadsheet is currently editable. I will make it, I will turn off editing as soon as class ends. So the expectation is you take 30 seconds to sign up for the attendance sheet each day just before or during lecture. Okay. Next Thursday, I will put up another link to Thursday's attendance sheet and so on. Okay, that's the syllabus. That's the course at a 10,000-foot view. Any questions?
I just have a comment to make. On the schedule, you put January. It's February.
Thank you very much. Excellent. Well done. And it's definitely not 2021. Tuesday, Thursday. Thank you. Good catch. What is that? That is the 9th and the 10th. Oh, no, sorry. How does that look? I think that's right. That looks right. Thank you very much. Any other questions, comments? Okay, glad to see you all. You're all awake this morning. Okay, so let's have a look at lecture 1. As I mentioned, this slide deck is also going to contain some sort of some more detailed logistics about the course, and we'll talk a little bit about why study robots at all. Hannah asks in chat, will group work be allowed on the final project? The short answer is no. I'd like you each to explore your own idea. However, I have absolutely no problem with you getting together with a group and sharing ideas about what works, what doesn't work, hacks and tips and tricks. But the idea in the final project is you have your own code base and you are free to take it in whatever direction you want. Sound good? Okay, so lecture 1, we're going to start with this somewhat enigmatic slide. Just a few weeks ago, an online news outlet reported what they considered the 4 biggest scientific breakthroughs of 2020. how many of these can you identify? If you know which scientific breakthroughs these images are meant to represent, go ahead and type the letter corresponding to that image into chat and what you think the scientific breakthrough is. Obviously, some of these are a little more obvious than others. I'll give you a minute to do that. Okay, right. So A should be pretty straightforward. It's not COVID actually. It's the COVID vaccine. So these are meant to represent scientific breakthroughs. Philip mentions protein folding for B. That's close. That's the problem actually. How do you solve the protein folding problem? There was an answer to that problem. That was reported in the scientific literature this year. Anybody remember what it is? So people are saying water discovered on Mars. Also not quite right. That's not Mars. Toby says the DeepMind protein folding. So Google has a research spin-off company called DeepMind. They presented a program, a machine learning program called AlphaFold. And AlphaFold can now solve, quote unquote solve, doesn't solve it perfectly, but it does much better at solving the protein folding problem than anything proposed so far. We won't talk about what the protein folding problem is in this class. Jack says possible water in Venus atmosphere. You got the right planet, but the wrong scientific breakthrough. The wrong scientific breakthrough. No? So I've forgotten now when in 2020, but a group of astronomers reported the detection of phosphine or phosphine, depending on how you pronounce it, in the atmosphere of Venus. And as far as we know, the only process that produces phosphine is life. So whether they actually detected phosphine and whether or not that phosphine is actually being emitted by organisms in the atmosphere of Venus remains to be seen, but you can understand why an online news outlet would consider this a pretty exciting scientific breakthrough, especially if it's true. Okay. The last one, D, I'm happy to report is something that my research group worked on. This is known as the xenobots, or living robots. These are evolved robots, and these evolved robots are not built from metal and ceramic and plastics. These millimeter wide robots are built from frog cells, more specifically the frog Xenopus laevis, thus the name xenobots. The first author who did most of the work on this project is Sam Kriegman. Sam is currently a PhD student in my lab, and Sam took this class maybe 4 or 5 years ago. So there is clearly a place for evolutionary robotics in the scientific landscape moving forward. I hope that some of you who are taking the class now will go on to also be involved in some pretty exciting scientific discoveries. Okay, we are going to talk about the Xenobots project itself, which is an evolutionary robotics project. We're going to talk about that in the very last lecture of the class. Okay. All right, so why study robots in the first place? Let's talk about the why, and then we'll talk about the how, or the nuts and bolts of robots. The most obvious answer is because robots are the coolest thing ever, and who wouldn't want to study robots? Okay. Aside from the fact that maybe they are just interesting in and of their own right, obviously robots are already emerging as incredibly useful tools. I use these 4 images to communicate my idea about one of the reasons why robots in general are so useful. What is the difference between the top pair of images and the bottom pair of images? We'll see if you can figure out what kind of message I'm communicating here. What is the rationale for why robots are useful? What's the difference between the top pair of images and the bottom pair of images? If you have an idea, go ahead and type it into chat. Okay, a lot of interesting ideas here. Matt says robots replacing work and robots assisting in work. So absolutely, in the top image, you can see that robot workers have displaced human workers, which is both a good and a bad thing. We'll talk about the ethics of robotics towards the end of the course. Aaron says the top images demonstrate an increase in efficiency. Absolutely, that's why robot workers replaced human workers. And the bottom increases safety. Okay, possibly. Similarly, George says replacing labor versus supplementing labor. Yeah, exactly. Interesting. There's some other differences. One that's kind of obvious is the two images in the top are both take place indoors, and the two images at the bottom take place out of doors. So let's talk about the top pair for a moment. Henry Ford, over 100 years ago, came up with the idea of mass production. So this was the idea that instead of having a single human artisan build an entire object, so instead of having one person sit down and make a basket or make a motorcycle all by themselves, it's better if you have a series of specialists, you have a whole bunch of workers distributed throughout an indoor space, and that indoor space became known as a factory. And each specialized worker performs one specialized action and then either moves the partly constructed machine to the next table or along a treadmill or along an assembly line, or the specialist walks to the next object, and so on. So the top left image is meant to represent mass production, which was the systematization of production or manufacture. That idea of specialization increasing efficiency, which was something that Aaron mentioned, many decades later, starting in the 1970s, with the beginnings of robotics, it became realized that you could create a specialized machine that replaced the specialized worker and would further accelerate the production of products. So mass production, systematized manufacture, industrial robotics, automated manufacture. Okay. Obviously, there were huge economic gains, but also economic and socio-economic disruptions for the workers who were no longer working in factories. So again, on the ethical and moral side, it's hard to say whether this was a good thing or a bad thing, but purely economically, this was a very, very good thing. So if robots are so useful at helping us build things indoors, where are the robots outdoors? So this is a picture I took, I think back in 2007. There was some construction going on campus. You'll notice that it's all people. There are machines on a construction site, but they are not autonomous machines. Remember, we are focused on this course on autonomous machines. An industrial robot is autonomous. It decides what to do and how to weld the car door on its own. All of the machines like diggers and steamrollers that you see on a construction site, they are machines, but they're not autonomous. There is someone literally driving the machine. If industrial robots are so useful to help us build things out of doors, why have we not deployed robots to automate the way we build things out of doors? Why don't we have robots building roads and bridges and skyscrapers? Safety, labor unions, yeah, very good point. Uncontrolled variables. So safety is a good one. We'll actually, so Shauna mentioned safety. We'll talk about safety a little bit later. Guaranteeing that a machine will act safely in close proximity to a human is still an open problem in robotics, but we can solve the safety problem by just firing all the workers, so replacing them with machines like we did in factories. Firing all the workers may not be an option for us because, as Logan mentioned, there are socioeconomic forces that may resist that. But as we have seen time and time again in Western cultures, if there is a good economic reason for doing something, socioeconomic forces and labor unions are only going to go so far. The real reason that we don't have robots yet on construction sites and building bridges and so on is related to what Matt said, which is uncontrolled variables. So if you think about a factory is by definition built to be a controlled environment. Inside a factory, the lighting always remains the same, the temperature remains the same, it never rains or snows inside a factory, which is good news for an industrial robot. If the industrial robot is trying to see a car door and determine where to weld that car door, if light levels are changing, it might make a mistake. Obviously, rain and snow are going to make things difficult. If there's a human in close proximity to the act of welding the car door, now there's safety issues. So we can build, basically, factories paved the way for robotics, but there is no equivalent of a factory the moment you step out of doors. The Greek philosopher Heraclitus said over 2,000 years ago, or is attributed to have said, "Man never enters the same river twice." If you think about your world and what you see from day to day, and admittedly in the pandemic era, the variability in your what you see every day has been reduced, but humans and animals constantly are dealing with changes in light level, changes in weather. You've probably sat in on 1,000 lectures and 1,000 courses by now, but they're all slightly different. We, meaning living beings, have had 4.5 billion years of practice of stepping into different rivers twice or 3 times or 4 times. We are evolved to adapt to changes in our environment, and robots are not. Industrial robots are actually designed to do the opposite. They are designed to do exactly the same thing over and over again in unchanging circumstances. Creating a robot that is efficient and useful at a construction site, and at the same time able to adapt to different construction sites in different places. Maybe there's a road in the middle of the construction site. Again, weather, people arrive, people leave, there's dust, changes in cost so that different materials are shipped in from different manufacturers. The tolerances and the I-beams of the metal beams that are being welded together are all changing. We don't yet know how to do that. We know how to build incredibly complex machines. We've built the International Space Station. We've built robotic factories. We've built these things. We know how to build complicated machines. We do not know how to build machines that are both autonomous, they don't have someone driving them, and at the same time are adaptive. And that's what evolutionary robotics is focused on. How do we make machines that are both autonomous and adaptive? And at the moment, it's an open question, and hopefully some of you may have some new ideas and contribute and advance this field. Okay. So why do we want robots on construction sites or outside? Because obviously they'd be helpful for construction. Another reason, those are sort of the engineering reasons for robotics. They could be extremely economically useful if we could ever figure out how to build adaptive and autonomous machines that work out of doors. Let's switch from engineering to science. Robotics is a branch of science. Robots are a tool to try and understand the nature of intelligence. Creating machines that are autonomous and adaptive, those machines are going to require some form of intelligence, and we haven't been able to distill down or understand what intelligence is well enough to be able to turn that definition of intelligence into code, put that code in a machine, and have that machine act autonomously and adaptively. So robotics is I would argue, one of the few open frontiers in science. There is no guiding theory yet about what intelligence is or how it should take form in a machine. If you look at a lot of other branches of the natural sciences, they are not necessarily open frontiers because they have a guiding theory that organizes investigation into that field. So in the case of biology, Darwinian descent with modification, or evolution, explains a lot of what happens in biology, and it guides the kinds of questions that are asked in biology. In the case of physics, both Newtonian and quantum mechanics taken together explain a lot of what happens in the physical world. And again, those frameworks of thought guide the questions that are asked in physics. It doesn't mean that biology is solved or physics is solved. There are still an infinite number of questions you can ask about biological or physical phenomenon, but there is a way to ask those questions. There is a similar guiding framework in chemistry. What is it? There's a lot that's known about chemistry, about the elements, and there's a guiding structure that supports chemistry and the kinds of questions you can ask in chemistry. What is that underlying framework? Most of us were introduced to this framework in high school, the periodic table. There's an underlying structure to the elements. They can be organized, which, if you think about it, is pretty surprising. They can be organized into a neat spreadsheet or a neat table that relates their properties to one another. What is the periodic table of intelligence? What is the equivalent of Newtonian and quantum mechanics for intelligence? Nobody knows. Now, that isn't to say that there haven't been some pretty breathtaking advances in artificial intelligence in just the last few years. We have started to figure out how to make deep neural networks that are very simple models of the brain that seem to work. They're able to recognize cats in YouTube videos and do a lot of other interesting things. Maybe the discoveries that we have made in the last few years is the beginnings of us uncovering an underlying framework with which to understand intelligence. Maybe. So it's an exciting time to get into the field of robotics and AI. It is sort of the Wild West, one of the few remaining frontiers in all of science. I personally believe there are several Nobel Prizes in AI and robotics that are waiting to be won. Maybe one of you will win one of them. Okay. Another thing that I think makes robotics intellectually exciting, it is one of the most interdisciplinary areas of study. In order to make progress on robotics, it is not enough to just be a good computer scientist or even just a good engineer. You'll see that a lot of work in robotics draws on many, many different fields. Obviously, in evolutionary robotics, we're going to draw a lot on evolutionary biology. If our robots are controlled by neural networks, which we'll talk about, you need to understand what neural networks are and what brains are. So we'll spend a fair bit of time dipping into neuroscience and cognitive science, psychology. Most of the autonomous and adaptive machines we're going to look at are also motile machines, meaning they're able to move themselves from point A to point B. How many of you have a Roomba at home? Roomba is an autonomous machine. It is also motile. The Roomba moves itself around. It's not really adaptive. How animals are able to move through their environment is this. Understanding that is the field of biomechanics. If we draw on biomechanics, maybe we can create robots that move quickly and efficiently and are able to adapt how they move and so on. We'll talk about some biomechanics later in the course. Obviously, computer science. We're going to do just a little bit of physics because we're going to have to. You're going to have to work with a physics engine throughout this course. So we're going to have to understand a little bit of physics. When we look at physical robots in lecture, Physical robots draw on all branches of engineering, mechanical engineering, electrical engineering. When we get into building living robots like the Xenobots, we get into bioengineering. We'll talk about bioengineering right at the end of the course. A lot of the robots you're going to see in this course are made from exotic materials, which takes us into chemistry and material science. There's a fair bit of math that underlies all AI and robotics. And finally, robotics often takes us into philosophy. What is intelligence? Question mark. This is a question that's existed in philosophy, and specifically in the philosophy of mind, for a long time. I would argue that one of our best tools for answering the question, what is intelligence, is a robot. A robot can be a useful and economic machine. A robot can also serve as a new kind of scientific tool. You think about a telescope and a microscope. With the invention of those technologies, scientists were able to answer or ask whole new kinds of questions. Same thing with robots. Okay, so carrying on with discussing why we might want to study robots, sort of back to the practical side of things. Obviously, one of the major challenges that our global society is wrestling with at the moment is climate change, which is inextricably linked with questions of energy. Our society uses more and more energy. How do we transition our society to be carbon neutral or carbon free? All of the solutions that have been proposed so far, like wind farms, solar farms, wave farms, tide farms, geothermal, they all require creating machines like solar panels or wind turbines or the tide worm that you see here. These machines have to autonomously track either tides or waves or wind or the sun. They have to rotate and follow whatever physical phenomenon that they are drawing energy from. So you can think of the wind farms and solar farms and wave farms and tide farms of the future as a swarm of robots. These robots may be non-self-motile. They are not actually moving themselves from point to point. But robotics is already a big part of creating a carbon-free economy. And that will just become more so in the years to come. Okay, so that's robots inside, outside, and of course, if we want to explore the depths of space, in a lot of cases, it will be robots rather than humans. There was an interesting post on Twitter I saw last week that somebody said their mind was blown when they realized Mars is a planet that is currently inhabited only by robots, which is true. How many robots are currently exploring the surface of Mars? Anybody know? It's a couple broken robots. It's about to be 3. Good point. Yes, there is another one that's arriving soon. Okay. That number is obviously probably going to increase in the years and decades to come. Yes, I mean physically on the surface. There are also robots, adaptive machines that are in orbit around the planet.
We're investigating how to use these really novel, tensile, soft, compliant, sort of more biologically inspired.
Sorry, let me start that again.
We're investigating how to use.
Okay, this is a particular robot design or set of robot designs that is currently on the drawing board at NASA. This is known as a Tensegrity Robot. I think I just restart. Oh, there we go. This is known as a Tensegrity Robot. You'll notice that it doesn't look like a normal kind of robot. You'll notice in this particular segment here, let's see if I can back up a little bit. You'll notice the advantage of tensegrity structure here. You have some valuable scientific instrument in the middle of the robot, and because of the way this robot is designed, on landing on a planetary surface, the physical structure of the robot buffers or softens the acceleration of this internal sensitive scientific instrument. Here are some of the members of the research team talking about this Tensegrity robot. There's another member of this research team, Nick Cheney, who worked on this project a few years back. Nick took this class about 10 years ago. Nick then went to go work for NASA on this project, and after NASA and doing a PhD, Nick returned here to UVM as a faculty member, and he will be teaching evolutionary algorithms. I'm not sure if it's this semester or next semester. So obviously a lot of interesting jobs out there. One last thing I want to say about the Tensegrity robot is I want you to think about the physical construction of this robot. How do you put together these rigid beams and connect them with wires or springs so that it either protects a scientific instrument, rolls to explore an environment. If it's in the bottom of a crater and has to climb the slope of the crater, what form should it take? Designing robots is a very non-intuitive practice. It's very difficult to do by hand. What we're going to see in this class is evolutionary algorithms are ideally suited for designing the body of the robot, how to put these bars together, and also how to evolve the brain of the robot, how to pull on these springs to get this robot to move. Okay, we're going to start to get into the details of evolutionary robotics here. For today's purposes, what I want you to take away is that there are basically 4 basic elements in every evolutionary robotics experiment we're going to explore in this class. The first one is the task environment. What is the world in which the robot exists? It may be a simulated world, it may be a physical world. It is the world that the robot draws on through its sensors, and it is the world that the robot pushes on with its motors. Obviously, in addition to the environment, we need the robot itself, the body of the robot, and then we have the brain, which for our purposes is going to be an artificial neural network. That artificial neural network is going to take incoming sensory values, transform them into outgoing motor commands. Okay. You then take these 3 elements and then we're going to wrap them in an evolutionary algorithm, and the evolutionary algorithm is going to modify the body and or brain of the robot to get it to do something useful. In this little cartoon here, what the evolutionary algorithm asked the robot to do is to figure out how to grasp this blue object in front of it and lift it onto its back. What I'm showing you in this video is a series of snapshots during an evolutionary algorithm. An evolutionary algorithm at the moment for our purposes is a trial and error process. It just tries out a whole bunch of solutions that do a little bit better at the task, which in this case is grasping and lifting the object. We make randomly modified copies of those robots, and those randomly modified copies overwrite the robots that didn't do a very good job at grasping and lifting the blue object in this case. So I'm only showing you the successful solutions along the way, not the failures or the mutated robots that didn't do a very good job. This is just to give you sort of a quick visual impression for how an evolutionary algorithm works. It's tinkering in this case with the brain inside the robot. It's not tinkering with the body at the moment, to get this robot to do a better and better job at lifting the blue object. So far so good? I apologize the second video isn't working, but not too important for our purposes today. Okay, I'll just pause for a moment. That's a lot of information so far. Any questions, comments, first impressions? No? Okay. Okay, back to logistics for a moment. That was sort of rationale about why you might want to study robotics. I should probably move this to a different part in the course, but come to class. Here's why. As I mentioned, here's some data showing that The more classes you miss, the less well you tend to do in this class. Okay. All right, so again, a little bit more logistics, just a little bit about who I am. I did my undergraduate in computer science in Canada. I then went to work for years as a software engineer. I found that industry was not the right place for me, so I returned to academia. I did a master's in evolutionary and adaptive systems at Sussex in England. This is a master's program that brought together biologists and computer scientists. And we studied the various points of contact between biology and computer science. One of those points of contact is evolutionary robotics. There's a lot of other points of contact, overlaps between biology and computer science. That was the one that I heard about as a master's student and got extremely interested in. I wanted to carry on work in this field of evolutionary robotics, so I went to go do my PhD with a professor at the University of Zurich in Switzerland, Rolf Pfeiffer, who was a pioneer in this area. After my PhD, I returned to North America and did a postdoc at Cornell for 3 years, where we worked on an evolutionary robotics project for NASA. Not the Tensegrity Robot that I just talked about, a different NASA project, and we'll talk about the results from that NASA project in a couple weeks' time. Okay, in 2006, I started up as a professor here at UVM. Okay, Logan has a question. What role does mathematical optimization play in this class? Yep, so an evolutionary algorithm is a form of optimization. It differs in many ways from reinforcement learning or classification and backpropagation of error. For those of you that have taken machine learning classes, you may have heard those terms before. If you haven't, that's okay. For those of you that are interested in how well an evolutionary algorithm does at optimization, that is a perfectly good thing to study in your final project. So Logan, for example, you may in your last 4 weeks use an evolutionary algorithm to optimize the behavior of a robot. You can then remove the evolutionary algorithm and replace it with reinforcement learning or another optimizer and compare how well these two different optimizers do at optimizing desired behavior for a given robot or set of robots. We're going to talk about evolutionary algorithms a little bit. We are not going to talk too much about which ones are better at optimization than others. That is a primary focus of the evolutionary computation class. So we're going to talk about it for maybe a class and a half, but it won't be a primary focus of this course. Okay, expectations. You're already providing feedback and asking questions in chat. That's great. Please do keep that up. I know it's easy as the semester starts to wear on and you've got a lot of things on your mind to just sort of sit back and let your eyes glaze over and listen to me drone on for 75 minutes. Much better if you try and stay focused by staying engaged with what we're discussing, posing questions or ideas into chat. You're never interrupting. In fact, it's the opposite. Please feel free to suggest ideas or ask questions at any time. Okay, common sense, I think that goes without saying. Regular but not necessarily perfect attendance, that 5% participation grade. As long as you miss 3 or fewer classes, you will get that 5% participation grade. If you find that you're missing 4, then 5, then 6 classes, so if you find you're missing more than 3 classes, come and see me before the end of the class, and we will both apply some common sense, and if you have a good reason for that, we'll figure something out. Okay. Best thing you can do is let Amanda and I know what's going on throughout the semester rather than asking for forgiveness at the end of the semester when we don't have a lot of options available to us. Okay. Hard work. You can ask students that have taken this class in previous years. It is a lot of coding, and the amount of coding increases throughout the 10 weeks. You got to stay on top of that, as well as the reading and lecture materials. Okay. There's no way that I can enforce memorization in a remote setting. I will, however, repeat many concepts over and over again, and we're going to look at lots of different examples that are meant to illustrate those concepts. So for example, when I just talked about the Tensegrity Robot, the concept that I introduced is the non-intuitiveness of designing robot structure. We're going to see that over and over again. Evolutionary algorithms are particularly useful optimizers because they can optimize the physical structure of the machine at the same time that they're optimizing the neural network controller of the machine. The Tensegrity Robot is one of dozens of examples of this non-intuitiveness of physical design that we're going to see throughout the course. So hopefully by repeating a lot of these concepts, you will memorize them and understand them and be able to give your own examples of them or point to your final project. The reason why I hope that you internalize the basic concepts of this class is that job interviews are closed book. You graduate from UVM, you're lucky enough to get a job interview at Google, and they ask about final projects. What did you do? What sort of project work did you do at UVM? You show them a YouTube video of your final project from this class, and you talk them through what they're looking at. You will, in your description, you will talk about the various concepts underlying evolutionary robotics. You'll have a lot of opportunity to be creative, especially in the last 4 weeks. The first 10 weeks, it's mostly implementation work, but you are definitely free to come up with your own ideas in the last 4 weeks. You'll see that there are prompts for a lot of self-learning in this class. You're going to maintain your code base using Git. If you haven't used Git before, neither Amanda nor I are going to teach you Git. We will point you to an online tutorial where you can teach yourself Git. Okay. Obviously, it goes without saying, we expect a positive attitude. Okay. What you cannot expect from me or the TA is help with your buggy code. So if you come to office hours and you screen share and you show us your code and you ask us why your program is crashing, Amanda and I will answer with, we don't know either. We will help talk you through it and help you become a better coder. We will help give you the tools you need to help debug your own code or answer your own question. Obviously, you don't need us for learning a programming language or installing software. There is a lot of material out there on the web. Okay. What you can expect from me is if there's certain concepts that come up during the coding that you're not familiar with, I'm happy to answer the why questions. Why do I need this? Why are we using Git versus something else? I'm happy to talk about those concepts with you, but again, we expect that you've consulted online resources. My hope is that the thing you take away from this class is an understanding of the conceptual issues and some of the open questions in evolutionary robotics. I don't expect you to memorize the detail of every experiment we see, or every robot we see. As I mentioned, all of the robots we're going to look at are meant to be examples or illustrations of certain concepts. Okay, if you're fuzzy on certain concepts, come and see me and Amanda, and we're happy to chat with you about what a genetic algorithm is, the role of mathematical optimization in this course, and so on. Feel free to ask about clarification at any time about assignments in the final project. And as I mentioned, there's going to be an emphasis in this class on concepts rather than specific tools. Because as you probably have already figured out in computer science, tools come and go all the time, but concepts change more slowly. You're gonna be programming in Python in this class. A few years back, we programmed in C++. You're going to be working with PyBullet physics engine in this class. Just last year, we used a different physics engine called ODE. Physics engines come and go, programming languages come and go, but being able to automatically design an autonomous machine is a concept and a challenge that has not been overcome in many decades. Okay, so we've got 12 minutes left. I want to talk about the nuts and bolts of how the programming projects go. All the material is on Blackboard, so if you go to Blackboard after class today, you'll see in course materials there's a Blackboard folder called assignments. In that Blackboard folder is an assignment called assignment 1. inside that Blackboard assignment 1, there will be a pointer to a subreddit called Ludobots. Ludobots is an online course that I run, and that online course shadows this course. So there are 60 of you that are taking this class here at UVM, and there will be an additional number, and I don't know how many, that will also be taking this class, but they will be taking it online only through Ludobots and not for credit. Okay, so I'm going to pop out a lecture for a moment. So if we go to Ludobots, you will see, here's the subreddit Ludobots, and you'll see there's a link that says start here. If you click on start here, it'll start you off on the very first part of assignment 1, known as step A. And step A is going to be nothing more than just installing the physics engine PyBullet, and there we go. Okay, step A has a grand total of 2 instructions here. Okay, so everything in the assignments is numbered so that if you come and see Amanda and I in office hours, we can very quickly get oriented to where you are. So for example, if you have problems installing PyBullet and you come and see Amanda or I later in the week, you can say, I'm working on assignment 1, step A2. So 1A2 is where you are and where you're stuck, right? Or 1A1 and so on. So just keep that in mind. That will help make things much more efficient in office hours. Okay. All right, so you start in Blackboard. Blackboard will take you to Ludobots, and in Ludobots you'll work your way through installation. As you do, you'll be creating a Git repository of your own, and this will contain all of your code that you develop over the 10 assignments. You can call your repository anything. A good name is probably CS206. Okay. Assignment 1 is made up of step A and step B. So if we go on to step B, which again, I guess it seems it's going to take a moment to bring up while it's loading. In step B, which is called simulation, so you're going to explore PyBullet simulation, you'll create a branch of your code base. So you're going to have a Git branch for each step in the online course Ludobots. If you're not familiar with Git, if you're not familiar with managing multiple branches of your repository, there is time this first week to learn that. So for those of you that are comfortable with Git, comfortable with Python, comfortable with installing software through pip, assignment 1 should probably take you half an hour or less. For those of you that are not so familiar with Git, you're going to have to learn Git and Git branches, learn how to install things through Python's installation program pip. Might take you much longer. So there's going to be a large variance in the amount of time that you all take to complete assignment 1. My apologies to those of you that are already have a lot of experience with Git and pip. You'll probably finish assignment 1 pretty quickly and be twiddling your thumbs until next Tuesday morning when I introduce assignment 2. Others, you might find that you're racing and putting a lot of time into assignment 1. As long as you feel comfortable with that and you learn what you need to learn about Git and pip and Python and so on, you're probably going to be okay in this class. Assignments 2 through 10, hopefully that variance will decrease. So this first week, we're trying to basically get everybody on the same page where you're creating Git branches as you complete each step in the 10 assignments. Any questions? So far, so good? Okay, so here's step B, simulation, and when you finish step B, you should have Python installed and you should have an empty simulation running. You'll see that this is not a video, this is a real-time physics engine. You can see me manipulating the virtual camera in that physics engine. When you finish step B, you are going to record a 5-second video of basically this. This is demonstrating that you have completed step B. In this course, you are not submitting any code. You're not submitting any code. You are submitting images and videos that prove that you have completed the code. Okay. Once you have completed step B and you've recorded a video of proof that you finished step B, you're going to upload that video that you just shot to YouTube. So we're going from Blackboard to Ludobots to YouTube. Your upload to YouTube is going to generate a YouTube link. You're going to create a Reddit post or a Reddit submission. And in that Reddit submission or that Reddit post, you're going to drop the YouTube link. So there's going to be a growing number of posts in the Ludobots subreddit, which are various students' solutions to step B. And all of those solutions point to various YouTube videos. And by looking at those videos, Amanda and I will be able to determine relatively quickly whether you implemented that particular step correctly or not. Obviously, all of the work that's in red and blue here, this is all within Reddit and YouTube. So both all of you, the UVM students, and all of the online students can do everything together in Reddit and YouTube. There's a final step in assignment 1 called One Link, and you'll see what that's about. When you finish step C, you'll generate a new YouTube video. Upload that. You'll upload that video to YouTube and submit a second post. So there's a post proving, you'll have a Reddit post proving that you finished B and a second Reddit post proving that you've completed step C. All of you will then take these two Reddit URLs, so pointers to your Reddit posts, and you will submit them in Blackboard. Blackboard is the gray. When Amanda and I go to grade your solution to assignment 1, we should see that your Blackboard submission has two links, Reddit submission B and Reddit submission C. We will click through to Reddit, click through to YouTube, watch your two videos and determine whether you successfully completed B or C. We will come back and give you a score out of 4. The assignment 1 is worth 4%. That will submit in Blackboard. So this shows you how I run this class at UVM and online in lockstep, but only you are submitting solutions in Blackboard for formal assessment. Okay, I realize this is a lot of information, but you'll go through it slowly as you implement steps A, B, and C in Reddit. Any questions? Any part of that you want me to repeat? Okay, so we have 3 minutes left. So what are you going to have at the end of 10 weeks? This is my best attempt to show an overall picture of what your code structure is going to look like at the end. This is what you're going to use in weeks 11, 12, 13, and 14 to evolve robots that walk or jump or pick up objects and put them on top of other objects. Whatever you end up doing for your final project, this will be your code base. I realize that this is probably completely unintelligible to you at the moment. That's perfectly fine. It won't be at the end of 10 weeks. In this first week, in assignment 1, you are going to install the physics engine we're going to be using, called PyBullet. You're going to be writing your own code, shown in black here. You're going to be writing a program called simulate.py, which starts up the simulator. Actually, you just saw me type in Python simulate.py, which opens up this empty simulator. You're then going to write, at the end of assignment 1, you're going to write a second Python program called generate, which is going to generate a set of objects that are going to make up your world. And PyroSim is a Python robot simulator. PyroSim is going to help you generate this world. And this world with a whole bunch of objects, sorry, I don't have the arrows here. Your generated objects that make up world 1 are going to be passed into PyBullet and into your simulator. And when you finish that, you will see a whole bunch of objects being constructed in the simulator. Okay. This is actually a snippet from assignment 2. You're not going to be placing these many objects in your simulator yet, but this is what you'll see. You'll see something similar to this with just one object at the end of assignment 1. Okay. So as we go throughout the course, and I explain the different assignments, you'll see there's links to these images as well. We're going to gradually reveal parts of this image, and at the end we will have revealed everything, and you'll have this, which is a code base that allows you to evolve simulated robots. Okay, we're out of time. Welcome again to CS 206. I've recorded today's lecture. I'll put it up on YouTube in an hour or two. You have a quiz that is due tonight at 11:59 p.m. I will put the quiz up on Blackboard around noon. And if you arrived late, please be sure to click on today's attendance sheet and mark yourself as here. Otherwise, I will see you all back here Thursday morning for our second lecture. Thanks very much, everybody. Have a great day.